Hi, everyone. I'm Samson Rainey from AGU's press office. Thank you for joining us this morning for our very first roundtable here at AbSciCon24 in Providence, where we'll hear about the latest on Venus water worries from a great slate of panelists. We'll begin with the panelists giving brief presentations describing their work, and then we'll open it up to questions from reporters. This format is meant to be more informal and conversational than a press conference, so we invite questions back and forth. Our discussion is being recorded and will be available to the public later today, posted on AGU's YouTube channel. For press, slides will be made available after the event. We'll end after an hour or when there are no more questions. All right, so now let's meet our panelists, both from the Laboratory for Atmospheric and Space Physics at the University of Colorado Boulder. We have Eryn, Cangi, and Michael Chaffin, both research scientists at LASP. All right, I'll turn it over to our panelists. Take it away.
Thanks very much. This is super exciting. This is the culmination of a lot of work that's been done over many years, and I'm excited to tell you about it. So if we could get the first slide. Now is a fantastic time to study water on Venus, to try to unravel the Venus water story. We're beginning what some people call the Decade of Venus, with a slate of missions planned by NASA and ESA. You can see the images for the NASA missions Veritas and Da Vinci, and the ESA mission Envision. All of these missions will make important, essential contributions to the study of water on Venus, with measurements of the surface that are indicative of present-day volcanism and the existence of possible past oceans, and measurements of water in the lower and middle atmosphere. Our work fits into this story by thinking about how that water was lost to space over time. Can we get the next slide, please? So there's this big mystery on Venus. Where did its water go? We think that Venus and Earth started out similar. They're very similar in size. They probably started off with similar amounts of water because they were formed from the same materials from the same region of the solar system. But today, Venus has only a 3-centimeter global equivalent layer of water in its atmosphere. You can imagine raining the water out of the Venus atmosphere and spreading it in an even layer, evenly over the surface. You would get a 3-centimeter layer of water, just barely enough to dip your toes in. Whereas on Earth today, we have 3 kilometers of water if you spread our oceans out equally around the surface. That's a difference of 100,000 between Earth and Venus. On the next slide, you can see a comparison of the size of Venus and Earth. As I mentioned, we think that Venus and Earth were born similar, but diverged. Today, Venus is incredibly hot. Its atmosphere is 90 times thicker than the Earth atmosphere, and liquid water cannot exist on Venus. All of the water on Venus is present in its atmosphere as vapor. You can also see that Venus is much more similar in size to the Earth than smaller Mars, which also experienced a water loss story that's different because of the lower gravity of the planet Mars. Can we get the next slide? So the question for why is the water abundance on Venus so low is that the water was lost. The answer to this question is the water was lost to space, either just after Venus's formation or following a period with Earth-like oceans. The million-dollar question in Venus exploration right now is whether Venus ever hosted oceans like the Earth's. It's possible that when water vapor was outgassed from the interior of Venus to form its initial atmosphere, that water vapor never condensed into liquid oceans and began to escape from the planet immediately. It's also possible that the oceans did condense, and then after a long period with Earth-like oceans, which might have been habitable, some cataclysm occurred, which drove the water into space, into the atmosphere, and then subsequently into space by a mechanism that Eryn will talk about. Can we get the next slide and cue Eryn up?
Behind. Okay, yeah, so as Mike talked about, there's these 2 different possible histories for Venus where it could have been, it could have had oceans on the surface, but may have also not had oceans on the surface. Next slide. So Mike mentioned this hydrodynamic escape, and this is the first method by which we think water was lost from Venus. So in this scenario where Venus had a steam atmosphere, incoming sunlight would have broken up water in the atmosphere into its components, so hydrogen and oxygen. That tends to really heat up the atmosphere, but in order to maintain some sort of thermal balance, that hydrogen needs to be ejected off into space as the planet attempts to cool itself. So that tends to remove hydrogen in a big sort of river out into space. But this is a self-limiting process, as you see there on the slide. It doesn't end up removing all of the water. At a certain point, once a lot of that hydrogen has been removed, this process will shut off, leaving the amount of about 10 to maybe 100, as much as 100 meters, again, global equivalent layer on the surface. But you can think of this as when you go to dump out your water bottle. If you dump most of the water into the sink, you've still got some drops left in there. So that's the amount of water that needs to be removed to explain the very low abundance that we have today, that 3 centimeters. And so our work here is showing that there's another escape process that hasn't been measured that explains how that extra water or that remaining water was lost. Let's go to the next slide. So as we said, the water on Venus is all in its atmosphere because of how hot Venus is. And so this is the process by which we can lose that water to space. So you've got that water in the atmosphere, the H2O, it ends up mixing with CO2 and does some chemistry in the upper atmosphere. And this produces a molecule called HCO+, which is an ion, so it has a positive charge. That ion in the atmosphere will combine with a free electron because opposites attract, as we all know. But when that happens, go ahead to the next slide, that resulting molecule has too much energy to remain combined and ends up breaking apart. So next slide. So that releases, oh, no, one back. Thank you. That releases the hydrogen atom from the new neutral HCO, and that hydrogen is able to escape to space. So our work has implications for the 2 scenarios that we talked about, both if there were oceans and if there were not. So next slide. So by considering this new process, this HCO dissociative recombination, which is the name, we've effectively doubled the amount of present day H escape that is going on versus what we thought was happening before. So one takeaway from this is that if you're losing hydrogen and therefore water faster today, you need less time to lose the water from Venus. And that means the oceans can stick around longer. Now that might sound a little counterintuitive because we're talking about losing the water. So a good analogy is if you are trying to get to the airport, you need to think about how fast you're going to drive or how fast is the method of transport you're going to use. If you get there really fast, you can stay at home for longer. So in this scenario, the oceans are you staying at home for longer. So in the real world here, this opens up the possible habitability of Venus to about another 1 billion years longer than we thought before. Next slide. So this is one of our plots from the paper that is showing what I just described here. So this HCO plus dissociative recombination process is quite important and produces a lot more escaping H, as you'll see on the left, than other methods that have used different, the other methods that have been studied in previous studies, excuse me. So this is showing how much H gets produced in the atmosphere at a given altitude. So the little blue section is showing that there's a lot coming from HCO plus recombination. On the right side, you'll see what I talked about with the possibility of having the oceans remain longer on the surface. So with the old mechanism, the red here, the published H loss rates are too slow to take us from what we thought happened in the past to what we can see happen today based on observations. But with our new mechanism here in blue, we reach the state that we are in today, and we also satisfy the constraints of what happened on Venus in the past. So again, just allows oceans to be present for longer on the surface.
If there ever were oceans.
If there were ever oceans, thank you. Yeah, we want to be very clear that we're not claiming that we found oceans in the past, just that if they were there, it enables this. Next slide. So if there were not oceans on the surface in the past, this instead would have an implication for what's going on with the release of gases from the surface or possibly from impacts from space. So if the water in the atmosphere is in a sort of steady state where the incoming matches the outgoing, then you would expect that a doubling of the escape rate now also implies a doubling of the supply of water into the Venus atmosphere. We did use some spacecraft data to work on this model, and specifically, we looked at the molecules that do the chemistry to form the HCO plus, because the previous spacecraft data do not actually measure HCO plus. No measurements exist of this molecule, but we do have the measurements of the ones that react to form it, and those do support the results that we've come up with in the model. But a new mission is needed, as stated, to measure the Venus upper atmosphere more, especially to take measurements of HCO plus more directly and confirm these results. This will also complete, or at least complement, the planned missions from NASA and ESA. Next slide. So once again, just going back, our future missions to Venus that we would really love to see would complement these planned missions that are coming up in the next decade of Venus. And this will help us complete the picture of water loss on Venus. Next slide.
And I think this is our last slide with conclusions.
Yes, yeah, we'll leave these up and.
Yeah, the bottom line is that Venus is an interconnected system where water from the interior is outgassed, perhaps today by active volcanism. By tracking that water through the lower atmosphere into the upper atmosphere and outward to space, we can bring a whole planet, whole atmosphere perspective to unraveling the story of Venus water, which helps us understand the water story on Earth-sized and Venus-sized planets throughout the universe, and understand how escape of water to space might limit the conditions for habitability everywhere. And I'm happy to take any questions. I'm sure Eryn is as well.
Yeah,
Yep.
well, thanks to our panelists for sharing your work. That was very exciting and impressive. I will now open it up to questions from reporters. As a reminder, only registered reporters may ask questions. If you would prefer to ask questions without speaking, type your complete question along with your name and affiliation in the chat, and we will ask it on your behalf. And we'll end the discussion after about 45 minutes, or when there are no more questions. So yeah, let's start.
I have
Faye?
one. Okay, well, thank you for a really interesting presentation. I'm Faye Flam. I write columns for Bloomberg, but I also write for other people. So I wondered if you could sort of, just to back up, talk about why you assume that Venus would have water, would have had water. Is it because it formed, you know, close enough to Earth and from the same clouds, so it would likely have incorporated the same basic mix of elements as our planet?
Yeah, so there have been dynamical models that assemble solar system like planets and track where the material came from according to our knowledge of the dynamics of that early disk from which the planets formed. And based on those simulations, what's called the feeding zone of Earth and Venus is fairly similar. That is, the material that formed both Earth and Venus came from similar regions within that protoplanetary disk, or the pre-planet disk. And that means that if you assemble Earth and Venus from the same materials, Earth and Venus should have the same water content and the same volatile content early on. But today, Venus is extremely dry, and that's the crux of this planetary mystery. How can you dry Venus out, even though they very likely formed with similar material?
Is it still thought that some of Earth's water had to come from comets or some other outside source?
This is a subject of active debate as to where exactly the material came from. But given how close Earth and Venus are in distance from the sun, regardless of where the material came from, whether it was formed locally, whether it was from icier asteroids further out, or comets even further out, the delivery to both Earth and Venus ought to have been similar.
Thank you.
Can I add one thing to that? So in addition to the models that Mike talked about and what we know about the formation of the planets, we also have observational data that suggests that there has been a lot of water on Venus in the past. We also have this at Mars, but there's something called the D to H ratio. So we talked about H escape to space, hydrogen escape to space. There's an isotope of hydrogen, which just means if you take a hydrogen atom and add in an extra nucleon, a neutral particle in the middle, you'll get something that behaves very similar to hydrogen, but is a little bit heavier, and that's called deuterium. So we actually have measurements of this deuterium to hydrogen ratio on Venus and Mars and Earth. And both Venus and Mars, I'll stick to Venus for now, have a very high ratio there. So Venus is about 120 times Earth. Now that's interesting because, like I said, deuterium is a little bit heavier than hydrogen. So when this escape process is going on, hydrogen is able to escape more easily than deuterium. So if you get a high value of D to H over time, that signifies that water has been lost, because just like we assume that it was formed from the same stuff, we assume that those ratios were similar on early Venus and present day Earth.
Thank you.
Let's see. I have a question about search for exoplanets. Does this study, do you think, widen the possibility of where we should be looking, or it has any kind of thoughts or implications for that?
So we are still in the pretty early days of looking at terrestrial exoplanet atmospheres, so atmospheres around Earth, like planets around other stars. And I believe this is not totally my area, but I believe there's still a lot of technological advancements to happen there. This does mean that we could look at, at a time when we get to that level of technological advancement, we can look at terrestrial planets on either side of the habitable zone. And that's this area in which a planet orbits a star in a region where water could exist on the surface in a liquid form, at least based on the
An Earth-like atmosphere.
an Earth-like atmosphere, with reasonable temperature and pressure conditions. Do you want to add anything to that?
I think you were about to talk about how Mars and Venus sample just outside what we think is the habitable zone. in
Yeah,
our
I think,
solar
sorry, I
system.
alluded to that, but didn't say it. So both Venus and Mars are just outside the habitable zone, but sort of on the edges. So there is a question about if that was different in the past. And of course, we see evidence for liquid water on Mars, although we don't really know if liquid water was ever on Venus.
Past liquid water.
Past Mars, yes,
ancient
thank you.
Flowing water on the surface of Mars.
Not right now, but we do see the surface features that were left over.
Yeah, I think what's really interesting to me with regard to comparing solar system planets and exoplanets is that we have a handful of terrestrial planets in our solar system, about which we will have way more data and higher quality data than we will probably ever get, at least within our lifetime, for exoplanets. And one thing that is very useful when doing solar system versus exoplanet studies is to compare, to think about these planets in our solar system as test points, and imagine planets that might exist intermediate to Venus and Earth, or to Earth and Mars, or to Venus and Mars. And the process that we talk about here in this paper for Venus is a fundamental chemical process that should occur on any planet that has CO2 and water in its atmosphere, and should remove water from those planets. And so in terms of potentially limiting habitability, this process is a process the process we talk about in this paper is one that could remove water from Earth-sized planets with Earth-like gravity. And so when we think about Earth-sized planets orbiting other stars, this process is one that could be very important in limiting the water availability within those planets' atmospheres and possibly on their surfaces.
I have a question from Aditi Ramakrishnan from AP. Are there any expected measurements from forthcoming Venus missions that would help paint a clearer picture of the water story on Venus, other than the HCO measurement?
Yeah, so some of these missions, I believe Da Vinci and Envision will measure that deuterium to hydrogen ratio I talked about a moment ago, through the bulk of the atmosphere. And by that, we mean at different altitudes in the atmosphere. We have some measurements of that so far from earlier Venus missions, but not as wide of array as data as we're expecting to get with the new missions. So that will help us understand the dynamics of deuterium to hydrogen in the atmosphere, like how it moves from the surface to space, perhaps back down in some cases like the deuterium. So that's going to fill in a picture of what's going on today, but it's not going to answer all of the questions, which is why we are really looking forward to potential future missions that will measure the HCO plus molecule and related processes such as the H escape.
Great.
Could you go back one slide to the one that we have with the planned missions? This is fun.
I will, okay.
There we are. Okay, cool. Yeah. So this is a really impressive slate of missions. I want to underscore that. These missions are doing critical science, and they'll help us understand the water story with measurements at the surface and the lower atmosphere and the clouds. People are calling this upcoming decade the decade of Venus because of these missions. They'll do fantastic science for water in the lower atmosphere, passage through the clouds to the base of the upper atmosphere, make surface measurements that are characteristic of that might help characterize a past ocean, understand the geological history of the planet and whether active volcanism is occurring today. And the one piece that our study contributes to these missions is better knowledge of the upper atmosphere and the processes that are taking the H and D, the hydrogen and the deuterium that are broken out of H2O, all the way out of the atmosphere to space. And it's through this added context that we're able to complement these missions, which will make fantastic measurements. I'm really looking forward to all of these and what we're going to learn about our sister planet. The thing that these missions won't measure is the upper atmosphere directly. And through this study, we found a process which has never been measured in the atmosphere of Venus. There are hints at it. It casts a shadow over data that was gathered by previous missions like Venus Express and Pioneer Venus Orbiter, for example. But there has never been a smoking gun for this particular process. And that's, for me, that would be a really fun measurement to make, to complement the existing measurements that are planned and complete the coverage of the atmosphere from surface to space in the decade of Venus, so that we can really dig in to how this atmosphere works and how the water story works there.
Great. I don't see any questions online. Any in the room?
Oh, I have another one.
Great.
How hot, this is probably naive, but how hot is it at the surface of Venus, and how do you get near it without your instruments being cooked or melted?
Yeah, I can answer the first part and perhaps the second part. So the temperature at the surface is, in science, we use kelvins, which is about 730 kelvins. But that's not very tangible. So I'll tell you also that it's about 800 degrees Fahrenheit, which is the temperature of a pizza oven. So yeah, rather hot and difficult to build instruments that will survive down there.
Hot enough to melt lead.
Yeah.
That's pretty hot.
Yeah.
Yes.
And it's 90 bars of atmosphere as
Yes,
well.
it's very
Yes.
high pressure.
So you essentially, like, if you want to get to the surface, you essentially have to build a heat tolerant submersible
Mhm.
and launch it into space and then descend through the atmosphere. And that's what Da Vinci is going to do. It's going to have a descent probe that'll make measurements in this lower, well-mixed atmosphere.
Yeah, of which we know very little. So that's gonna be really excellent. But the previous probe from Pioneer Venus, I think, as you might expect, did not survive for very long on the surface because of the very high condition, of the very high pressure and high temperature conditions.
And the Soviet Venera missions landed on the surface and returned some data from the surface. But there was no way for the components to operate long-term. And so there's an active research project, engineering research project, about how to make a long-term station work on the surface of Venus. Could you do a rover on the surface of Venus, say? Maybe in the distant future with some of these technological advancements that they're working on.
Question from Charles Blue.
Yes, hi, Charles Blue, Planetary Science Division with NASA. I am curious, what can be done remotely with, say, millimeter wavelength spectra or other non-probe missions that could help suss out some of the more intriguing elements in the upper atmosphere of Venus? I know there was recent studies with ALMA that have been inconclusive at the time, but do those capabilities at all provide data that would be helpful in your research?
Sure, yeah, I can take a stab at it, even though I'm not a submillimeter astronomer and I don't do ground-based astronomy. The submillimeter is a really rich spectroscopic range that's diagnostic of a lot of molecules. There's been fantastic work done on Mars with submillimeter astronomy, for example. A lot of work done on Venus as well, let's say Sophia and ALMA and other observatories. The trick with measurements made from Earth is that you're looking through the Earth's atmosphere and then down into the Venus atmosphere. The processes that we're talking about occur at the very top of the Venus atmosphere. So the telescope observations, mostly what they see is the atmosphere that's below where these processes are occurring. It may be possible, again, I'm not an expert, to isolate spectral lines of upper atmospheric compounds and then probe those processes more directly. But the gas is so tenuous at these high altitudes that what's really valuable is having a measurement from closer where you can look across the atmosphere instead of straight down, or with direct measurements dipping down into the atmosphere and say using mass spectroscopy to understand what's there directly, to taste the atmosphere, if you want a sense analogy.
Of course, the water in the atmosphere attenuates submillimeter wavelengths anyway, so maybe that would kind of include trying to search that molecule, or is that, are there tracers that could provide data as well?
So this is my ignorance, but I don't know what's been done with water in the submillimeter on Venus. I know that there are telescopic observations which have constrained the deuterium to hydrogen ratio in water from the Earth. One of two key measurements, the other from the Pioneer Venus Orbiter Descent Probe, that tell us what the D to H ratio is in water on Venus and our record of these loss processes happening over time. Yeah, certainly ground-based and space-based Earth observations from Earth would be very valuable. There have been limited telescopic observations of the very upper atmosphere on Venus that get at direct measurements of hydrogen and deuterium. The problem with telescope observations of Venus, of course, is that the sun is right there. And so for space-based observatories like the Hubble Space Telescope, they worry a lot about pointing the telescope close to the sun. And that limits the availability of observation conditions at Earth that would allow us to measure the upper atmosphere from space-based assets orbiting Earth.
And I'll add, since I think you also said general remote sensing, what Mike talked about looking at the atmosphere across on a line that goes sort of across parallel to the surface, more or less. That's something we do at Mars with the Mars Atmosphere and Volatile Evolution mission, on which we're both on. So with that, we can use our ultraviolet spectrograph to look at the ultraviolet emissions from hydrogen and deuterium in the atmosphere of Mars, to get their abundances and also to get at the escape. So that's also related to the question of water. So if we were to have something like that at Venus, that would be a similar remote sensing measurement that we could make. But again, that requires putting something in orbit around Venus. It's always a trade-off between, you know, cost to put something in space versus the quality of the data you can get.
Great. Okay, any other questions online? Don't see any questions online. Any other questions in the room?
Daniel Hudon, Boston University. I wonder, excuse me, could you reiterate HCO plus as a diagnostic for your study?
Sure.
So the water vapor in the atmosphere gets dissociated, and then how is HCO plus actually a diagnostic for?
Yeah, so the water in the atmosphere ends up going through chemistry where it mixes with CO2, undergoes some reactions there, and then forms the HCO plus molecule. So ultimately, the source of the hydrogen on Venus is the
In
water
the HCO plus, yeah.
Yes, sorry, the hydrogen in HCO plus is ultimately coming from the water molecule. So that's why we can go from water to HCO plus to hydrogen escape and say this is the pathway that tells us about the water loss.
But we don't expect the hydrogen to escape already?
We don't expect it.
Once it's dissociated, wouldn't the hydrogen escape?
So some of it also can do that as well, but so the process I described is where the water has not yet dissociated. Some of it will combine with CO2 to go through this chemical process. If the water dissociates into, say, H and then OH, some of that atomic hydrogen could also just escape on its own, yes.
But on Venus, the gravity is large enough that that direct escape channel is totally shut down at present. It's only in the early, or under early conditions where the hydrogen content of the atmosphere is very large that you get enough heating of the atmosphere to drive direct loss. So that's the distinction between like this early hydrodynamic loss period where you get fluid outflow that removes most of the water content, and our process takes over and removes the last drops of water from the atmosphere. But if you think about it in terms of fractions, you remove a large fraction of the initial water through hydrodynamic escape. Then of what's left over, you need to remove an even larger fraction to arrive at the present day state. And that last bit of loss is accomplished by this mechanism that we found is nearly equal to all of the other processes that remove water from the atmosphere today put together.
Yeah, thanks for the clarification. I was conflating two time periods in my mind.
Great. Any other questions online? Any other questions in the room?
And, excuse me, and it's also feasible because there's little circulation on Venus.
So Venus is an interesting test case for a couple of reasons. One is that it's the same size as the Earth, very similar mass. Another is that it rotates very slowly.
Yeah.
So a day on Venus is longer than a year on Venus. And this means that Venus because Venus doesn't rotate very quickly, there's an intense difference between day and night. This difference is something that needs to be taken into account when you try to understand how the loss processes operate. So the modeling that we did in this paper is a one-dimensional model. There's a saying in planetary modeling that all models are wrong, some models are useful. So we chose, we implemented this model in a way that it gave us a result which we think is applicable to the real 3D atmosphere. And we confirmed that by looking at the limited existing data from the Pioneer Venus orbiter, which suggests that our model is in the right ballpark. But one interesting thing in the Pioneer Venus data is there's this big difference in water loss from the day side versus the night side of the planet. Actually, the Pioneer Venus orbiter data predicts that the water loss should be much larger on the night side than it is on the day side. And this is the kind of thing that you would need more sophisticated models, but ultimately direct measurements to be able to investigate so that we can tell, where does water loss occur from Venus? Is it on the day side or on the night side? Is our modeling giving us something that's correct within an order of magnitude, within a factor of 2, and that order of magnitude or factor of 2 goes directly into reconstructing the timing of the water story on Venus and when water escape would have needed to start in order to deplete the atmosphere to its present dry state by the present day.
I see no other questions online. Any last final question in the room? Great. Well, we'll end it there today. Thanks to everyone for joining us here and online. Our next press event will be tomorrow at 11:30, where we'll have a roundtable discussion about the Europa Clipper mission. You'll see a copy of this event on AG's YouTube later today, and a copy of the slides will be sent to journalists momentarily. Thank you.